I'm joined this afternoon by Dr. Hrachowitz, who's kindly agreed to talk to me about his really interesting paper in the journal Nature and Climate Change, all about how precipitation shifts from snow towards rain are leading to a decrease in stream flow. So thank you very much for joining me, Ross.
No problem.
It's a very interesting paper. It was very a lot in there, so I just wondered if you would just break it down for me a little bit.
Mm-hmm.
First of all, I'm interested, what motivated you into starting this study?
It was an accident, really. It was one of those classic moments in science when we were looking at something and we stumbled across something else. So this is work I was doing with a PhD student of mine, and so he deserves lots of the credit for it. He'd been studying the hydrology of about 400 catchments in the US, and he'd plotted the data from these catchments, the river flow and the rainfall and the potential evaporation, in a particular way that showed up something that we found hard to understand, something that looked a bit curious.
That's always the way in science, isn't it? You start off in one direction and then it takes you...
And then you see something strange, you say, what's going on there?
Yeah.
So perhaps I can show you on this figure.
Yep, please do.
So this figure is what we call a Boudico plot. So there are plots like this in lots of different fields of science. So sometimes, like, you know, the plot that you draw, you could imagine where you were looking at people's heights and weights, that the taller people are, the heavier you'd expect them to be. Although if I told you what height someone was, you couldn't guess exactly what weight they were, but you'd know on average probably if they're a bit higher, then they're probably a bit heavier. So you have it in medicine, you have the same sort of thing in astronomy. So for stars, if you know what colour they are, then you can figure out typically how bright they are, how much energy they're radiating. You can tell that just from the colour. So we do the same kind of thing in hydrology. And along one axis, this axis along here, we plot the dryness of the climate. So catchments down this end are very wet. So along this axis we're plotting the ratio, how much energy is there to evaporate water divided by how much precipitation is coming in. So that's the wet end, and down here is the very dry end. So the dry places, these are like deserts, places like that where it's nice and hot and there's lots of energy available to evaporate water and it doesn't rain very much, relatively speaking. And down this end are the wet ones like the mountains in Scotland or the west coast of the South Island in New Zealand or somewhere like that. So this is the dryness. And what we typically expect is, as you go from wetter catchments to drier catchments along this axis, as you go along this direction, you expect the amount of river flow that's generated in these catchments to go down in a systematic way. And that's what we typically find. And up this axis here, we're plotting what we call the evaporative index. So this represents how much of the precipitation becomes river flow versus how much of it's evaporated. So down here we have high river flow, and up the top here we have very low river flow. And so most catchments on this graph are around this line here. And so you can see lots of them scattered around this line, and this is very typical behaviour, and this is what we call a Boudico curve.
I see.
So what we expect to find is these 400 catchments we looked at, that they'd all plot around this curve, but they didn't. See all these ones here? Well, when we looked at them, we thought they shouldn't be there. What's going on here? There's something unusual, and this is the moment where we saw something strange. So we weren't particularly looking for this, we just noticed it and said, how can this be? What's the explanation?
Okay, so this was the start of the journey then?
Absolutely. This was the moment when we thought, that's something interesting. I wonder why that happens. Okay. And so at this point, I asked Wouter, what do you think's going on here? And he was the one who then went away and looked at all sorts of possible explanations for what might be going on. And it turned out that the further we were below the Boudico curve, the further down this way we were, the more snow there was in these places.
Okay.
Okay, so if you take all of the precipitation that falls over a long period of time and you separate it out according to whether it fell as snow or it fell as rain, that's a number we call the snow fraction.
Right, okay.
Okay, and so as you go down here, the snow fraction tends to get larger and larger the further away from this curve. So what we've drawn on this picture here is we've just coloured in all of the catchments, so
Right.
one dot for each catchment, and if it's red, then there's more than 15% snow, like these ones, and if it's green, it means less than 15% snow. And what you can see right here is that most of the green ones are up here near the Boudica curve, where they should be,
Yeah.
and the red ones, there's a tendency for red ones to be below the curve.
Okay, so there's something going on with the snow fraction then.
That's what we thought. So at this point here, we could see that snow was a possible explanation for this, and we hadn't found anything else that could be. But we weren't really sure exactly what was going on, because it could have been something else that's correlated with snow, so that something that happens in places that have lots of snow that was actually the explanation for this. It could have been nothing to do with snow, we didn't really know.
Okay.
So because, for example, it snows quite a lot in the mountains, so it might have been that the real cause of this was the steepness of the land.
Right.
Because mountains tend to be steep and mountains have lots of snow, so maybe it was steepness rather than snow. So then we did another piece of analysis to try and figure out whether it was snow or whether it was something else. And that's what I'd like to show you on the next figure. Okay, so now what we did was, instead of looking at 400 different catchments and seeing what was going on in different catchments, we took each catchment separately and looked at the different years. And we said, in the years where there's more snow, so we made another graph, and along this axis here, we plotted this snow fraction, the ratio of the amount of snow to the total amount of precipitation. So here it's low, and over here it's high.
Yeah.
And up here, how much river flow. And each of these dots on this graph is from a different year. And because what we'd seen in the previous figure was that the catchments that had the bigger snow fractions were further below that Boudica curve. That meant, on that graph at least, catchments with more snow were making more stream flow. What we wanted to check here was, in years with more snow, so as we go down this end, do we get more stream flow? So we just drew a dot for each year, and then we made the best fit line through all of those points, and we said, what's the slope of this line? And if the slope of that line's positive, that means that more snow means more stream flow. If that slope of that line had been flat, that would say there's no relation at all.
Okay.
Or if there'd been negative, it would be, well, actually, if you compare different years, it's round the other way.
Okay.
And what we found was that for 94 out of the 97 snowy catchments, the slope of this line was positive, and for the other 3, it was positive but very close to 0. So we couldn't be sure whether, for those 3, whether it was 0 or slightly positive. But none of them were negative at all. So what that said was the same thing that was going on in the previous picture when we compared between when we compared between catchments, was also going on when you compare between years. And what that means is that we can eliminate lots of the possible explanations for the first figure. So because this is something that's going on between different years, it must be something to do with the weather. It's not to do with topography, for example, because in each of these years, you've got the same topography.
Right, yes.
So it can't be, whatever effect we found, it's not explained by topography, it's something to do with the weather, and it looks like it's something to do with snow. So where we'd got to at the end of that was that we'd found that in places where more precipitation falls as snow, you get more stream flow, and in years with more precipitation falling as snow, you get more stream flow.
Okay, that's interesting. So what are the implications of this finding?
This is important for understanding the impacts of climate change.
Right.
Because what we're expecting with climate change is that temperatures will get warmer. When the temperatures get warmer, on average, the fraction of precipitation that falls as snow will go down, because for it to snow, it needs to be cold enough. And so because the temperature is going to get warmer, it's going to be less often that there'll be really cold days in wintertime. So the snow fraction will go down. And because what we've shown is that in years with low snow fraction have lower stream flow, what we expect under climate change would be that in future we'd expect less stream flow than we have now as a fraction of precipitation. And if there's less stream flow, that means there's less water available for humans and for the ecosystem.
Wow, so it's quite an impact on society and on...
Yes, and it turns out that we did an estimate of approximately how big is this effect. And for 2 degrees warming for a typical catchment from the data set that we studied, it's a loss of flow of somewhere between about 10% and 25%.
Wow.
And it's more in drier catchments.
Right.
So somewhere between 10 and 25%, which is enough that this might actually be something quite significant.
Goodness me. So do you have any idea what's causing this? What the mechanism is behind this?
We have lots of ideas about what it might be, but we don't really know, to be honest, what the answer is. So we've made a long list of possible explanations for this. At the moment, we don't think that there's going to be a single story that explains this everywhere, because these catchments that we studied in the US, they're in lots of different places in the US with different types of snowy climates and different types of hydrological processes that are important. So probably there's not just one answer to this question. So we think the answer's going to be, it's complicated.
Okay. And so are you still working on this? How are you taking this forward?
So we're taking this forward on a number of different angles. One of the things we're doing is repeating the same study in other places, because it would be very reassuring to know that this wasn't something that was specific to one data set. So I've put together a team of partners who have data from about 15 other countries, and we're all planning to repeat the same analysis together for lots of other places to see whether it happens in somewhere else apart from here. So that's the first step. And then the second step is to try and figure out why this happens. And so we've got this list of about 7 or 8 different hypotheses for why this might be. And we're going to test those hypotheses in a couple of different ways. One is by getting some other colleagues who have detailed field data where they've measured hydrological processes in snowy places, and they've got data in years with more snow and data in years with less snow. And so we can try and see exactly what was going on inside those catchments from a measurement point of view. And the other approach we're going to take is using computer simulation models. So we've got one particular computer model in mind that has lots of different hydrology models built inside it. So you can try out lots and lots of different combinations of exactly how to represent hydrological processes. The reason for doing that is because at the moment we're still not really confident about exactly how to model a lot of the details of what goes on inside a catchment. And so we're going to try lots of different methods in a search for the computer models that are able to reproduce the effect that we see, where you get less stream flow in years with less snow. And then once we find the models that can do that, we'll then be able to look inside the model and say, exactly how did that happen? How did the computer move the water around inside that catchment? Which processes were responsible for it being able to produce less stream flow in the years with less snow? So that will give us another line of evidence. I don't think any of those by themselves will be enough, but the plan is to put together the field data, the field observations, along with the computer models to try and figure out which are the processes that cause this to happen.
Okay, wow, that sounds absolutely fascinating. Thank you, Ross, for spending time with me and discussing these findings. Thank you very much.
You're welcome.